Hi, I'm Dr. Jigluri, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, I will discuss about the question bank on magnetic materials and superconducting properties. So, the problem one is calculate magnetization and magnetic flux density if magnetic field intensity is 250 ampere per meter and relative permeability is 15. So, this problem comes under the Bloom's taxonomy level of apply. So the course outcome is CO5. So here the learner is to recall and apply. The learner is to apply the problems, that is formulas. So for the solving the magnetic flux density and then magnetization, so that it comes under the Bloom's taxonomy level of apply. So the problem is calculate magnetization and magnetic flux density if magnetic field intensity is 250 ampere per meter and the relative permeability is 15. So let's write the given data. So magnetic field intensity. So magnetic field intensity H is equals to 250 ampere per meter. And then relative permeability. So relative permeability mu R is equals to 15. We have to calculate magnetization and then magnetic flux density. So need to calculate magnetization, that is M, and then magnetic flux density. Magnetic flux density, so P is equals to, we need to calculate it. So we know that mu naught, so mu naught, so permeability of free space, mu naught is equals to 4 pi into 10 power minus 7 Henry per meter. So first we should calculate the magnetic flux density. So magnetic flux density formula is B is equals to mu H. So that is H is the magnetic field intensity, mu is the permeability, B is the magnetic flux density. So we don't know the permeability mu value. We don't know the permeability mu value. So that we are going to write the relation between mu naught and mu r. So the relation between mu naught, mu r is equals to mu naught, mu r. So from this relation I am writing mu is equals to mu naught, mu r into H. So that we can substitute the permeability of free space and also relative permeability from the problem. So B is equals to 4 pi into 10 power minus 7 into 15 into H is 250 ampere per meter. So this magnetic flux density becomes B is equals to 47.12 into 10 power minus 4 Tesla. So this is the magnetic flux density value. And also we have to calculate the magnetization. So formula for the magnetization is M is equals to chi into H. That is, chi is equals to M by H. We know susceptibility. From the susceptibility, chi is equals to M by H. From this, M is equals to chi into H. So this is magnetization. So from this magnetization, M is equals to chi H. So here it is the magnetization. And this is magnetic field intensity. So chi is the susceptibility of the material. So M is equals to chi is 14 into 250. So it is equals to 3500 ampere per meter. So how we can calculate this chi value? Chi have the relation chi susceptibility. So susceptibility chi is equals to mu r minus 1. Mu r we know 15 minus 1. So it is equals to 14. So M is equals to chi into H. Chi is 14. So 14 into 250 is equals to 3500 ampere per meter. So find relative permeability if H is equals to 220 ampere per meter and M is equals to 3300 ampere per meter. So the data, H is magnetic field intensity. Magnetic field intensity. Right. Magnetic field intensity, H is equals to 220 amperes per meter, and magnetization M is equals to 3300 ampere per meter. So we have to calculate the relative permeability mu r. Mu r we need to calculate. So that mu r is equals to, as we know that from the susceptibility is equals to chi is equals to mu r minus 1. So from this mu r is equals to one plus chi. So what is this chi? So relation we can take from this is a relation between chi mu r and chi and mu r. So from the relation between susceptibility and magnetization, so chi is equals to m by h. So from this, to find the susceptibility, we have h and m. So that m is 3300 divided by 220. So ampere per meter and then ampere per meter. So it is equals to 15. So chi, susceptibility, chi is equals to 15. So from this, we have to calculate the relative permeability. So this is the relative permeability. So relative permeability, mu r is equals to 1 plus chi. So it is equals to 1 plus 15 is equals to 60. This is mu r. This is the relative permeability value if h is equals to 220 ampere per meter and m is equals to 3300 ampere per meter. The magnetic susceptibility of aluminium is 2.3 into 10 power minus 5. Find its permeability and relative permeability. So this problem belongs to the apply level of Bloom's taxonomy and the course outcome is CO5. So here the given data is susceptibility, magnetic susceptibility of aluminium, and we need to calculate the permeability and then relative permeability. So the given data is susceptibility of the aluminium. Chi is equals to 2.3 into 10 power minus 5. So we have to calculate the permeability. So permeability mu and then relative permeability mu r. So to find the relative permeability, we have the formula. Mu r is equals to 1 plus chi. So mu r is equals to 1 plus 2.3 into 10 power minus 5. So it is equals to 1.000023. Mu r relative permeability is equals to 1.000023. And by using this, we can calculate the permeability. So permeability formula is mu is equals to mu naught into mu r. So mu naught is 4 pi into 10 power minus 7 Henry per meter into mu r. Now we calculated. So 1.000023. So it is equals to 12.566 into 10 power minus 7 Henry per meter. This is the permeability of the aluminium. Next one. If a magnetic field of strength 300 ampere per meter produces a magnetization of 4200 ampere per meter in a ferromagnetic material, find the relative permeability of the material. So this comes under the applying level of Bloom's taxonomy So once again we can see the problem. So if your magnetic field of strength 300 ampere per meter produces a magnetization of 4200 ampere per meter in a ferromagnetic material, find the relative permeability of the material. So the data given in the problem is magnetic field strength, that is magnetic field intensity. So the magnetic field strength magnetic field strength capital H, so that is equals to 300 ampere per meter. Magnetization of the material is capital M is equals to 4200 ampere per meter. So we need to find the relative permeability of the material. So relative permeability we need to calculate. So to find the relative permeability, first we should know the susceptibility value. So as we know that M and H, that is magnetization we know, and then H also given in the problem. So the relation between chi and MH is chi is equals to M by H. So from that we calculate the susceptibility chi value. So then from the formula mu r is equals to 1 plus chi. So we can find the value of mu r by substituting chi value in the mu r formula. So the formula susceptibility chi is equals to M by H. So M is 4200 ampere per meter divided by 300 ampere per meter. So it is equals to 14. So chi is equals to magnetic susceptibility chi is equals to 14. Then to find the relative permeability of the material. So the formula for relative permeability of the material mu r is equals to 1 plus chi. So just now we calculated chi value. So let's substitute mu r relative permeability. Mu r is equals to 1 plus 14. So mu r is equals to 50. This is the relative permeability of the given ferromagnetic material. So next problem, a paramagnetic material has a magnetic field intensity of 10 power 4 ampere per meter. If the susceptibility of the material at room temperature is 3.7 into 10 power minus 3, calculate the magnetization and magnetic flux density in the material. So magnetization we need to calculate and the magnetic flux density also we need to calculate. So this problem belongs to the applying level of Bloom's taxonomy. So here in this problem, the given data are magnetic field intensity. So the magnetic field intensity is denoted with the capital H. So H is equals to 10 power 4 ampere per meter. And then the susceptibility, that is the susceptibility of the material at room temperature is 3.7 into 10 power minus 3. So susceptibility chi is equals to 3.7 into 10 power minus 3. which is at room temperature. And then we need to calculate the magnetization and the magnetic flux density. So magnetization M, we need to calculate, and then magnetic flux density. B is equals to how much? So here the magnetization formula for magnetization, so M is equals to chi into H, where it is from chi is equals to M by H. So this implies magnetization M is equals to chi into H. So M is equals to chi is 3.7 into 10 power minus 3 into the magnetic field intensity or magnetic field strength 10 power 4. So it is equals to 37 ampere per meter. This is the magnetization. M is equals to 37 ampere per meter. So, and also we need to calculate the magnetic flux density. So formula for magnetic flux density, B is equals to mu H. So mu is equals to mu naught mu r into H. So it is equals to mu naught is 4 pi into 10 power minus 7 mu r. So mu r is equals to 1 plus chi. So chi also given here. So mu r directly I am writing here. Mu r is equals to 1 plus chi. So mu r is equals to 1 plus chi into H. So let's substitute 4 pi into 10 power minus 7 into 1 plus chi is 3.7 into 10 power minus 3 into H is power 4. 10 power 4. So B is equals to mu naught mu r H. So mu naught mu r is 1 plus chi into H. So mu naught is 4 pi into 10 power minus 7 into 1 plus 3.7 into 10 power minus 3. H is 10 power 4. So it is equals to 0.0126 Web per meter square. So this is the value of magnetic flux density of a material. So the next problem is the transition temperature for plumber is equals to 7.2 degree Kelvin. However, at 5 degree Kelvin, it loses the superconducting property if subjected to magnetic field of 3.3 into 10 power 4 ampere per meter. Find the maximum value of H which will allow the metal to retain its superconductivity at 0 degree Kelvin. So this problem belongs to applying level of Bloom's taxonomy. So because here the learner should apply the formulas. So let's see the problem. Transition temperature. So transition temperature of PB is 7.2 degree Kelvin. So transition temperature or critical temperature of TC is equals to 7.2 degree Kelvin. And then critical magnetic field, that is it loses the superconducting property if it is subjected to the magnetic field. So where the superconductor, where the superconductor loses its superconducting property and changes to normal conductor. So that particular magnetic field is called the critical magnetic field. So critical magnetic field Hc is equals to 3.3 into 10 power 4 ampere per meter. So where the temperature T is equals to 5 degree Kelvin. So we need to calculate the maximum value of H, which will allow the metal to retain its superconductivity at 0 degree Kelvin. So we have to calculate the H, maximum value of H. So the formula is, so we need to calculate the maximum value of magnetic field, maximum value of H at 0 degree Kelvin. So maximum value of magnetic field at 0 degree Kelvin, that is H naught, we need to calculate. So the formula to find H naught, so critical magnetic field is equals to, H naught is equals to Hc by 1 minus T by Tc whole square. So we will get H naught is equals to Hc by 1 minus T by Tc square. So 3.3 into 10 power 4 divided by 1 minus 5 by 7.2 square. So it is equals to 3.3 into 10 power 4 divided by 1 minus 25 by 51.84. So while calculating, we'll get 6.37 into 10 power 4 ampere per meter, which is the maximum magnetic field at 0 degree Kelvin. Next, the critical magnetic field, the critical field of niobium is 1 into 10 power 5 ampere per meter and at 8 degree Kelvin, and 2 into 10 power 5 ampere per meter at 0 degree Kelvin. Calculate the transition temperature of the element. So this is also comes under the Bloom's taxonomy level of apply. So here the learner has to apply the formulas for transition temperature. So the critical magnetic field, that is critical magnetic field, has been given. So that is equals to Hc. Hc is equals to 1 into 10 power 5 ampere per meter, which is at the temperature T is equals to 8 degree Kelvin. Then 2 into 10 power 5 ampere per meter at 0 degree Kelvin. So H naught is equals to 2 into 10 power 5 ampere per meter. Now we need to calculate the transition temperature of the element Tc. So Tc is equals to, what is the degree Kelvin? So formula to find the transition temperature or critical temperature, Tc is equals to Tc is equals to T by 1 minus Hc by H naught over 1 by 2. So it is equals to 8 by 1 minus, that is 1 into 10 power 5 divided by 2 into 10 power 5 power 1 by 2. So it is equals to 11.3 degree Kelvin. So transition temperature is equals to Tc is equals to 11.3 degree Kelvin. Tc. Next problem. The critical magnetic field at 5 degree Kelvin is 2 into 10 power 3 ampere per meter in a superconductor ring of radius 0.02 meters. Find the value of critical current. Find the value of critical current. This is also comes under the applying level of Bloom's taxonomy. So the data given in the problem. So critical magnetic field. Critical magnetic field Hc is equals to 2 into 10 power 3 ampere per meter. So which is at the temperature T is equals to 5 degree Kelvin. 5 degree Kelvin. So radius of the ring also given. So radius of the ring. So R is equals to 0.02 meters. 0.02 meters. So we have to find the critical current value. So critical current IC is equals to how much? So formula for finding the critical current IC is equals to 2 pi R HC. So where R is the radius of the ring and HC is the critical magnetic field. So IC is equals to critical current IC is equals to 2 into pi is 3.143. Radius of the ring is 0.02 meters and critical current is 2 into 10 power 3 ampere per meter. So IC becomes, when calculating, 251.4 amperes. So this is the value of critical current to this problem. The next problem is superconducting tin has a critical current of 3.7 degree Kelvin at a zero magnetic field and a critical field of 0.0306 at 0 degree Kelvin. So 0.0306 Tesla at 0 degree Kelvin. Find a critical field at 2 degree Kelvin. Find a critical current also if R is equals to 1. This is also applying level of Bloom's taxonomy. So that is given data in this problem. So critical current, critical temperature. So critical temperature of the superconducting material tin. So Tc is equals to 3.7, critical temperature 3.7 degree Kelvin. So at a zero magnetic field. So critical field of 0.0306 Tesla at 0 degree Kelvin. So critical field is given. So critical field Hc is equals to 0.0306. So this critical field is at 0 degree Kelvin. So H naught is equals to 0.0306 Tesla. So temperature T is equals to 0 degree Kelvin. So we have to find the critical field at a 2 degree Kelvin. So we have to find the critical field Hc is equals to at a 2 degree Kelvin. So find critical current also if radius r is equals to 1 meter. So critical current also we have to calculate. So from this we use the formula. So critical magnetic field Hc is equals to H naught into 1 minus T square by Tc square. So it is equals to and IC critical current IC is equals to 2 pi R Hc. These are the formulas we are going to use to find the values of critical current and critical magnetic field and then critical current. So using the critical magnetic field, so Hc is equals to H naught into 1 minus T square by Tc square. So Hc critical magnetic field is equals to H naught is 0.0306 into 1 minus 2 square by 3.7 square. So Hc becomes 0.02166 ampere per meter. But while coming to the critical current, IC is equals to 2 pi R Hc. So 2 into 3.143 into radius is 1 meter. So into Hc is 0.02166 ampere per meter. So it is equals to 0.136 amperes. This is the critical current IC. Next, coming to the next problem, calculate the critical current for a wire of lead having a diameter of 1 millimeter at 4.2 degree Kelvin. The critical temperature for lead is 7.18 degree Kelvin and the critical magnetic field at 0 degree Kelvin is 6.5 into 10 power 4 ampere per meter. So applying level of Bloom's taxonomy. This one belongs to applying level of Bloom's taxonomy. So the given data in the problem. So critical current. So critical current of your wire of lead having diameter 1 millimeter at 4.2 degree Kelvin. So we need to calculate the IC. The critical temperature for a lead. So critical temperature means Tc. So Tc is given. So 7.18 degree Kelvin and a critical magnetic field. So critical magnetic field at a 0 degree Kelvin. So H naught is equals to H naught is equals to 6.5 into 10 power 4 ampere per meter. So diameter of the wire. So diameter of the wire D is equals to 1 millimeter. So it is equals to R is equals to D by 2 is equals to 1 by 2 into 10 power minus 3 meters. So we need to calculate the IC. So formulas we use. Critical magnetic field is equals to H naught into 1 minus T square by Tc square, and then critical current IC is equals to 2 pi R Hc. So let's substitute in the values. Hc is equals to H naught is 6.5 into 10 power 4 into 1 minus 4.2 whole square divided by 7.19 square. So it is equals to 42.758 into 10 power 3 ampere per meter. Then critical current IC is equals to 2 pi r HC. 2 into 3.143 into 0.5 into 10 power minus 3 into 42.758 into 10 power 3. So critical current IC becomes 134.26 amperes. So these are the values of critical magnetic field and then critical current of the given problem. So let's see the references. So engineering physics by K. Tyagarajan, McGraw Education Private Limited, New Delhi. A textbook of engineering physics by M.N. Avadhanulu, P.G. Ksheerasagar, S. Chand and Company, New Delhi. Engineering physics by Dr. M. Arhugam, Anuradha Publications, Chennai, 6,70,000. Engineering physics by P.K. Palanisamy, 4th edition, SciTech Publication, India Private Limited, Chennai, 6,70,000. These are the reference books. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.